Assalamu alaikum wa rahmatullahi wa barakatuh. This week, inshallah, we are going to implement experiment number 4, which is all about the diodes, the regular diode and the Zener diode. We are going to implement 3 different circuits that include diode and Zener diodes and Zener diodes. Before we start any of the circuits, the first thing to know about the diodes that you will see in the lab is that the diode that you usually use this symbol for, it looks like this in the lab. It looks like a cylinder, black cylinder with a silver line. So it's black cylinder, all black, with a silver line at one of the ends. And this silver line tells you where the negative terminal of the diode. So if this is in your symbol, in the symbol that you use in the course, this is the symbol of the diode, this is the negative side, and this is the positive side. So the silver line, this silver line tells you that the negative terminal of the diode is this terminal and the positive terminal is the other terminal. So the regular diode, it looks like a black cylinder, I'm going to show you the component now. Hopefully it will appear in front of the camera with a silver line like this. While the Zener diode, which we usually use this symbol for, this is the Zener. In the lab, it looks like a golden cylinder. So it's a golden cylinder with a black line towards the negative terminal. So this is golden. I'm going to color the golden here like red. It's a golden cylinder with black line towards the negative terminal. So if this is the negative terminal, the black line here will be towards the negative terminal, while the other terminal is the positive one. So this is how the diodes they look like in the lab. So the regular diode looks like this. Hopefully you see it. It's a black cylinder with silver line towards the negative terminal, while the Zener diode, it looks like this. It's a red or golden component, red or golden cylinder with a black line towards the negative terminal. We have 2 types of Zener diodes. We have Zener diode with a breakdown voltage of 5.1 and another Zener diode with a breakdown voltage that ranges between 2.1 and 3.6. The one that we are going to use in our lab is the smaller one with breakdown between 2.1 and 3.6, and I'll explain why later. So the big one here is the one, the big Zener diode is the one with the 5.1 breakdown, while the other one is the Zener diode with breakdown between 2.1 and 3.6. We are going to use the smaller one for our experiment here. Okay, the first circuit that we are going to implement is a logic circuit or a logic gate that looks like this. We are going to connect a DC 5 volt to a resistor 4 kilo ohm, and then we are going to connect here 2 regular diodes in this direction, the positive in this side and the negative in this side. Of course, in the lab components you have to connect the regular diode with the line, with the silver line in this side. Okay, we are going here to connect 2 voltages, volt VA to this terminal and volt VB to this terminal, and we are going to measure the output from here. The voltages that we are connecting here, VA and VB, these are DC voltages, so we are going to use the DC sources attached to our board, and we are going to connect either 0 or 5 for VA and 0 or 5 for VB. One time we connect 0 here, or 0 here and 5 here, or 5 and 0, or 5 and 5. And then we are going to build a truth table. And in each case we measure V out. So when VA is 0 and VB is 0, what is V output? When VA is 0 and VB is 5, what is V output? 5 and 0, what is V output? 5 and 5, what is V output? And from this truth table, we need to identify which gate, which logic gate is this. So from the truth table, we need to identify which logic gate is this. So here we are going to connect DC 5 volt, and here also we are going to connect DC voltage from the voltage source, DC voltage source attached to the board, but we are going one time to use here 0 or 5 and here 0 or 5. This will give us 4 combinations as you see in the table. So this is the first circuit to implement. The second circuit that we are going to implement is, probably you have studied in the lecture. It looks like this. We have an AC source, we have a diode, and then we have a resistor. This is a regular diode so far, and we have a resistor of 1 kilo ohm, and this is the ground. Our AC source here, we will use a 10 volt peak to peak source with 5 kilohertz frequency. 10 volt peak to peak means what? Means that the peak of the source will be 5 volt. The peak in one side 5 and the other side is -5. So this is 10 volt peak to peak. And this is, by the way, this is the maximum that we can get from our function generator in the lab. We cannot increase the voltage coming from the function generator above 10 volt peak to peak. And then for this circuit, we are going to measure V output between this point and the ground. So basically, we are going to connect channel 2 of the oscilloscope, between this terminal and this terminal. So channel 2 will be connected here. What about channel 1? We said many times before that by default, channel 1 is connected to the input source, to the function generator. So by default, channel 1 will be connected here. So channel 1 of the oscilloscope, by default, it is connected to the function generator. So now we have channel 1 here to the input, channel 2 to the output. This is our output voltage. And then what is required here? We are required to plot the relation between V output and V input. We are required to see on the oscilloscope, we need to see a relation between V output and V input. Not between V input and time, not between V output and time. We need to see a figure on the oscilloscope between V output and V input. And how to do this? We talked about this in the first lab, in the first week. We said that if you want to plot V output against V input, channel 2 against channel 1, you have to use something called XY mode. And how to reach to the XY mode from the oscilloscope? We said that you need to press on the button called utility, then display. Once you press on the button called utility, you will find on the screen that there is an option called display, and from display you choose XY mode. The XY mode will give you a plot between channel 2 and channel 1. Channel 1 on the horizontal axis and channel 2 on the vertical axis. But it is important when you use the XY mode, as we said before, it's important to have the same scale, the same voltage scale for both channels. So use same scale for both channels. And it is recommended here, maybe use 0.5 volt per division, okay, for channel 1 and for channel 2. Both of them, they have to be the same. Okay, so let me see. So this is what is required in the first step of this circuit. In the second step, we are going to flip the diode. We are going to flip the direction of the diode. So instead of having the diode in this direction, we are going to have the diode in this direction. Okay, and we repeat the experiment. So we are going to sketch another figure between V output and V input. So when we flip the diode, we are going to plot another figure between V output and V input. One more thing about the XY mode is that you need to set, as we said, we need to set the same scale for V output and V input, and additionally you need to set the position. Use the position button of channel 1 and channel 2 and set the positions to 0. So position of both channels must be set to 0. And you can do that by changing the position button on the oscilloscope until you see 0 that appears on the oscilloscope for channel 1, and then you change the position of channel 2 until you see 0 on the oscilloscope. Changing the position to 0 guarantees that on the screen of the oscilloscope, the origin of the plot will be exactly in the center of the screen. Okay, so changing the position to 0 and 0, this means that the origin of your plot, the origin of your figure, will be exactly in the middle of the screen. Okay, so this is the purpose of having the position to be 0 for both channels. Right. So this is the second step. So far we have two figures. We need to plot this figure when the diode in this direction, this figure when the diode in the opposite direction. And then the next step is we are going to replace this diode with a Zener diode. So we are going to use here a Zener diode in this direction, only in this direction. And for the Zener diode, ya shabab, we are going to plot two figures. I'm going to remove this for now. For the Zener diode, we are going to plot two figures. The first figure is we are going to plot V output against time. Using the oscilloscope, of course. Now, when I say plot, this means you sketch the what you see on the oscilloscope. So you need to see on the oscilloscope V output against time, and you need to plot also V output against V input. So here you will use XY mode, while here you are going to use the regular plot, which is the YT mode or XT mode. YT mode. YT means you are plotting a signal against time. XY mode, you are plotting a signal against another signal. Okay? So for the Zener diode in this direction, we are going to plot two figures. So far total we have four figures. For the regular diode in this direction, V output against V input. For the regular diode in the other direction, V output against V input. Here, for the Zener diode in this direction, we need to plot V output against time, and we need to plot V output against V input. Also, for this step, you can do a nice experiment. You can start with small V input. So you can start with a function generator, like with 1 volt peak to peak, and you keep increasing it. In the beginning, you will notice that you have a V output that appears with a certain shape, and then as you increase V input, you will notice that V output is going to change shape after a certain limit. When the magnitude of V input increases above a certain limit, the output will change shape. What is the reason for that? What's the reason? Is when you increase V input, at certain point, V input will be enough to break down the Zener diode in the negative side, of course. When the V input, this is AC, half of the cycle it's positive, half of the cycle it's negative. At a certain magnitude, the negative cycle here will be enough to break down the Zener diode, causes the output to change. So it's important to notice here at what value V output is going to change. So in the beginning, when, for example, let me give you an example. In the beginning, when V input is 1 volt peak to peak or 2 volt peak to peak, for example, okay, you will find that the Zener diode is going to operate only in the positive half cycle, so it's going to give you something like this. Okay, While if you increase V input more, what happens is that instead of having 0 V output in the negative half cycle, the Zener diode is going to break down. The Zener diode is going to break down, and then V output is going to give you something in the negative half cycle. This is something I will leave. I will not give you the exact result here, but I will leave it to you to do by yourself, okay, and see during the implementation. So here for the Zener diode in this direction, we are going to plot 2 plots. First plot V output against time, and then you show me as you increase V input, what is the value of V output, what's the value of V input at which V output is going to change shape. And then you sketch here you sketch the shape of V output for V input equals 10 volt peak to peak. So the sketch itself, it will be for V input peak to peak 10 volt. But you keep increasing it, and you see at which value of V input V output is going to change. Also, you need to plot V output against V input. So now for this circuit, we have 4 figures to plot. Let's move now to the next circuit. The next circuit is purely Zener diode. So the next circuit looks like this. AC source, and then resistor here, which is 1 kilo ohm. Then we'll have 2 Zener diodes connected in opposite directions. So this is the first Zener diode, and this is the second Zener diode. So 2 Zener diodes, and as we said, we are going to use here the small Zener diode with a breakdown that ranges between 2.1 and 3.6. So the output here will be measured across this is our ground, okay, and this is our source. Again, we'll use V input 10 volt peak to peak and 5 kilohertz frequency. By default, channel 1 of the oscilloscope is connected to the function generator, and we are going to connect channel 2 of the oscilloscope here between these 2 terminals, and this will represent our output. Okay? So for this circuit, ya shabab, we need to plot again 2 plots. The first plot, we need to plot V output against time. So we need to see how V output against time looks like. Okay, and we need also to plot V output against V input. So we need to plot another figure of V output against V input. Okay, of course you studied this circuit. I believe you studied this circuit in the course, and you know that this branch, it will be open circuit most of the time, unless this branch is going to be open circuit, unless the input voltage is enough to operate this diode in the forward region and break down this diode, right? So this branch is going to be open circuit. This branch is going to be open circuit unless V input is enough to operate this diode in the forward region. And we know that a Zener diode in the forward region, it works like a regular diode. So it needs around 0.6 or 0.7, let's say 0.7 to operate in the forward region. And in order to break down this diode, we need around 2.1 volt. We are using the small Zener diode here. So total we need in order for this branch to operate, you need around 2.8 volt, maybe more, because the breakdown of the Zener diode, it ranges between 2.1 up to 3.6. So you will need between 2.8 total you will need between 2.8 up to 4.3 volt to operate this branch. When this branch operates, it will give you constant V output. So when V input reaches high values above above, let's say 2.8, you expect that V output is going to give you constant. Same on the other side. When V input is below negative 2.8, V output is going to give you constant volt. What about in between? In between, this branch is going to be open circuit and V output will be equal to V input. So this is what you expect to see for a circuit like this. So for this circuit, we need to plot V output against time, and V output, I will leave this to you, and I gave you a hint here about how V output against V input looks like. So total, we need 6 figures for our experiment. Before we finish, let me tell you why we used here the 2.1, the small Zener diode. Why we didn't use the big Zener diode with 5.1 volt. If we used here the big Zener diode with 5.1 volt, assume that we use here 5.1 volt Zener diode that breaks down at 5.1 volt, would we be able to operate this branch ever? In this case, if we use the 5.1 volt breakdown Zener diode here, we will need, in order for this branch to operate, we will need around 5.8 volt total, 5.1 to break down this diode and 0.7 to operate this diode in the forward region. So we need total, for this branch, we need 5.8 volt. However, our function generator, maximum, it gives us peak of 5. The peak of the voltage coming from the function generator from our source, it's 5 peak. 10 peak to peak. 10 peak to peak means that the peak is 5, right? So 5 will not be enough to operate this branch in this case. That's why we don't use the large Zener diode, because it will not break down. This circuit will not operate, it will not work, right? It will be always open circuit. Always it will be open circuit. Right? That's why we don't use the 5.1 here, because we need, in order for this branch to operate, and you see the function of the circuit, you need at least 5.8 volt peak from the source. But the source gives you maximum 5. So if it gives you maximum 5, this branch will be always open circuit and it will not operate. That's why we don't use 5.1 Zener diode, and we use the smaller Zener diode, which ranges between 2.1 to 3.6 volt breakdown. Okay, Shabab, so total we have 3 circuits, we have 6 figures, and we have a truth table. Okay, so this is what we need to do in our experiment today. Let me see if we have any more information about this. Don't forget, for the XY mode, we need to use same scale. We have to use same scale for both channels. And also, we need to set the position of both channels to 0. Okay? Fine. So that's it. And we'll see you in the next video, where we are going to implement practically the 3 circuits that we talked about. See you in the next video.